Welcome to today's webinar titled Hyperspectral Infrared Imaging of Fugitive Methane Emissions from Flare Stacks, brought to you by Telops. As a reminder, the recording of today's presentation, along with the PDF of the slide deck, will be sent to you via email later this afternoon. If you have any questions for the presenter during the presentation, please use the Q&A button at the bottom of your screen to type your question at any time. Questions will be answered at the end of the presentation. I'd like to introduce to you today's speaker, Dr. Mark Norman. Dr. Norman is a Telops field applications engineer based in Boston, Massachusetts. For over 22 years, he has worked in the area of detection and identification of hazardous chemicals for civilian and military emergency response agencies. He holds a PhD in analytical chemistry from the University of North Carolina at Chapel Hill. In his current role, Dr. Norman provides technical support to customers utilizing Telops hyperspectral and broadband infrared imaging cameras for a range of applications, including fluid dynamics, methane detection, combustion analysis, and fire research. Please join me in welcoming Dr. Norman.
Thank you, Jessica, for that introduction, and hello to everyone out there in webinar land. I'm very pleased to be with you today to present this discussion on hyperspectral infrared imaging of methane emissions from flare stacks. And it's my great pleasure to hopefully teach you something about what we at Telops are doing in the area of infrared imaging, and to help you learn how it may benefit you in what you do in your work. So the story for today is shown here in the webinar outline. Whenever I give a presentation or a training, I like to tell a story. And my goal is for each of you to take something away, at least one thing away that you didn't know when we started this today. So take notes and take consideration of the topics I'll be covering. So first, I'm going to give a very brief overview of Telops and the product line that we offer for infrared cameras. And I'm going to then go into the hyperspectral imaging basics. Now, it's a mouthful, hyperspectral imaging. If you're not familiar with it, it's a very powerful technique. I'm going to go into the very basics so that you understand how it contributes to what we do in terms of airborne methane detection and some of the capabilities and limitations that are associated with that. Further on, I'm going to go into the HyperCam Airborne Mini. Now, this is the device that we use for these airborne measurements, and I'll go into some of the details of how it operates and some of the considerations that we must make when it comes to setting up a system for your airborne measurements. Then I'm going to talk about a service that Telops offers in the area of LDAR, leak detection and repair, specifically for methane and those measurements that are necessary. And if you're on this webinar today, you're probably interested in how you or your agency can get more information about methane emissions, fugitive emissions in particular, and how you can utilize that information to better your business practices. The real heart of this webinar is in a campaign that we did this past February with a partner where we actually measured some fugitive methane emissions. So I'm going to talk about how we set that up and how we conducted the measurements and some of the results that we got as a case study on what we can do for you as a business. I'm going to start to wrap up by talking about the next generation of where this technology is going. And then towards the end, we'll cover some questions and answers as time permits. But again, take some time to think about, as I go through this presentation, what can you learn that you didn't know right now when we get started? So real quick on Telops. So Telops is a company based in Quebec City, Canada. Beautiful city, Never been there, I recommend taking a trip. But it was started back in 2000, so 23 years they've been in business. And we now employ over 90 people, many with highly technical degrees, such as myself. And over the years, Teleops has established itself as a leader in infrared imaging solutions. And really, in the next slide, when I show you an overview of the product line, I think you'll appreciate that our mission as a company is to provide high performance systems for very demanding applications that require high speed acquisition, high dynamic range conditions, and in the case of the hyperspectral cameras, high spectral resolution. So with that, this is a very brief overview of the product line. So starting from the left, you can see an example of our latest in the line of hyperspectral cameras. And I'm going to get into what hyperspectral means in just a moment. But these are cameras that are infrared sensitive and provide the highest in spectral resolution for chemical analysis. As you move towards the right on this slide, you see that we have a line of multispectral cameras. Now, these are broadband infrared cameras, but they incorporate filters, either broadband or narrowband, bandpass filters, what have you, to provide some degree of chemical specificity, but at relatively high speed. In the middle, you see an example, little video playing of our high dynamic range version of the camera, which can allow you to image the scenes which have very high infrared emission characteristics to very low, if you will, very dark situations. As we go toward the right, you see our very fast cameras, and these can be used to acquire infrared images over 100,000 frames per second. So very fast imaging, if that is the need for your application. And then towards the right, we have our entry-level cameras for more basic applications if a customer is in the need for infrared imaging, but not the need for the terribly high performance that the other cameras offer. So I just wanted to give you a flavor for these cameras. The reason they're called cooled IR cameras is because in the infrared, generally speaking, the detector has to be cooled so that it's sensitive to the infrared radiation that it is designed to collect. All right, let's get into hyperspectral cameras. And there's a lot on this slide, and I just want you to get the main message. And the message here is about FTIR technology, also Fourier transform infrared. So in an FTIR, which is a technology that's been around for decades at this point, there are three key optical components, as you see in the figure on the left. There is a mirror, which is fixed in position. There's another mirror, which moves, and there's a beam splitter between them. That's the green sort of diagonal element you see in the photo. Now, what happens is infrared radiation, in this case for our cameras, comes in to the camera from the background, from the sun, just whatever is in the environment. That radiation is directed to these mirrors, and the moving mirror goes back and forth. Now, as that moving mirror translates, the radiation from the fixed mirror and the moving mirror recombine at the beam splitter, and then they go to the detector, the FPA, or focal plane array. Now, what happens here is, in time, the different energies or the different wavelengths of infrared are encoded or modulated as they reach the detector. And what we actually measure at the detector at every single pixel of this detector is what's called an interferogram. So this is a signal of intensity as a function of time. Now, as I mentioned, it's at each pixel. So what happens with the detector is at every pixel, this interferogram is collected, and then this mathematical process called the fast Fourier transform is applied. And that converts this time domain signal into what we call the frequency domain, or a term that I'm going to use throughout this presentation, the wave number domain. That is what creates the spectrum. Now, the spectrum is what we can use as scientists to do chemical analysis. And what's very interesting here is that because we're collecting this spectral data at every pixel within the FPA, we're creating what's called a hypercube. I know it sounds very science fiction, but a hypercube is nothing more than a full infrared spectrum at every pixel of the FPA. And what's really cool is this spectral data that we collect, it contains the fundamental absorption or emission characteristics of the gas of interest. In the case we're talking about today, methane. So it's a fundamental technique to really get a chemical picture of the gas of interest when we're collecting the data. Now, some of the key benefits of using FTIR, it's fairly fast. We can collect hypercubes in less than a second. Very specific, because the data we collect, as you see in the little inset in the image, the spectrum of methane has peaks that are characteristic to just methane. But it does much more than methane. We can do different volatile organic compounds and nitrous oxide, sulfur dioxide, what have you. And the other nice thing, as I'll talk, is it relates to quantification. We can actually quantify the amount of gas that is being detected in the hypercube. And the point I want to make in the very last bullet is this technique, FTIR, within the forensic science community, is actually recognized as what's called a Category A technique. I won't go into the details there, but what that means is FTIR has very high fidelity, very high reproducibility, and a very, very low rate of false responses. So it's a powerful technique for chemical analysis, FTIR, and that's what we use in the hyperspectral systems. And the system I'm discussing today is called the HyperCam Airborne Mini. Now, just some specifications. I won't read through all of them in the interest of time, but it's relatively compact and lightweight, less than 50 pounds, very amenable to installation on an aircraft, as I'll discuss, for the airborne measurements. Again, it has this focal plane array detector. It has what are called black bodies, which are used to calibrate the response, so you get the most accurate measurements in the intensity of the response. It also has a visible camera integrated, so as you're flying your missions, you'll get visible images that are in conjunction with the infrared images that are being collected. There is a stabilization platform you see on the bottom of the picture on the left, and that keeps the system stable. It dampens vibrations and allows the system to gimbal or to rotate an angle as needed to collect the data. Again, detection, identification is done in real time. I'll talk about quantification, which is something we do post-processing with the data that's collected. But the important thing here is the modes of operation. And I'm going to talk about this more in the next slide, but there are two modes we call mapping and targeting. And you choose the mode of interest based on what you need to achieve in your measurement campaign. So just a very quick overview of the HyperCam Airborne Mini, which is the device we're talking about today, which was used for the measurement campaign back in February. All right, let's talk about these modes of operation. So there are really two. I said mapping and targeting. And the mapping is really divided into both area mapping and corridor mapping. Basically, what that means is that using a set of GPS coordinates, you can program the device to fly over, for example, a natural gas transmission pipeline. And as you're flying over it, the device, based on GPS, will collect data along that pipeline. Or you can do an area where you specify a region, and then maybe as you fly back and forth and zigzag over that area, you collect data throughout the mission. What I'm going to be talking about today are experiments we did in the targeting mode, which is similar, but really means that we specify a single GPS coordinate, so a target of interest. And as we fly over that, the system is designed to collect data both forward, over, and back on that coordinate. So in both cases of these types of modes, the system automatically collects the data. So in pre-planning, working with us, you program the GPS coordinates you want to investigate, and the system does all the work. And the software we use is called Reveal Airborne Planner. And the Reveal name is what we use for our suite of software for all the different products that we manufacture. But the bottom line is, working with us, you decide, how do I want to do my measurement? We help you program the coordinates, set the flight plans. You fly the aircraft, the system does the rest in either of these types of modes. So let me talk a little bit about our leak detection and repair measurement services. Now, we're not in the business of repair, but in terms of detection and finding methane, that's what we can help you do. And if you work with teleops, okay, what are your responsibilities? Well, you provide the aircraft and the flight crew. It could be a Cessna, it could be a helicopter, as you'll see later on in the presentation. It could be an unmanned drone, UAV. We don't have those facilities. We work with you to either identify what you need or work with contractors who can do that. You participate in the planning, as I discussed. Where do you want to do the measurements? What are the coordinates you need to inspect? And then ultimately, you or your agency fly the missions and collect the data. What do we do at teleops? Well, we provide all the hardware and the software, rugged laptop, and we train the operators on how to do all the operations. We help you in the pre-flight planning, and then we're there on site as you're doing these measurements. We take all the data, we post-process it, we do the quantification, and then ultimately we give you a final report. And as you can see in the image that is shown on the left, this is an example of a type of measurement where methane is detected in this targeting mode. This is a generic description of a type of measurement, but you see the types of things we can do. And the bottom line is, it's a team effort. We work with you to do these types of airborne measurements, specifically for methane in the LDAR business. All right, so enough about teleops and what we provide. Let's get into the meat of what we're here to learn about today. So back in February, some colleagues and I went out to Livermore, California, and we worked with an agency, Skycam Aviation, and they actually do airborne measurements using visible imagery. They were interested in what they could do with infrared imagery. So we partnered with them, did some pre-planning, and took a system out there and spent a week at their site. As you see in the upper left, they have a Cessna 182. And in this aircraft, they have an 8-inch bore in the fuselage to allow for the imaging down below as they're flying. And the system I described, the Hypercam Airborne Mini, has a GPS antenna, which we attach to the back window. You can sort of see it in the photo. And that allows the system to track when it needs to make the measurements. In this case, Skycam provided the battery power for the operation, and it allowed for about 2 hours of continuous operation of the Hypercam Airborne Mini. In the flight planning, they wanted to do a couple different above ground level, or AGL, measurements, as is shown here. And they flew the aircraft at a speed of 70 knots. The way we set up the Hypercam Airborne Mini for these measurements was we operated at 10 wave number resolution. Now, for you, that might not mean anything, but all it means is the lower that number, the wave number, the finer the peaks are in the measured data, and the higher the number, the faster you can collect data. So we did an optimization and decided 10 wave numbers was perfectly sufficient to detect methane, and we wanted to collect data at less than 1 hypercube per second. So that's how we configured the system for this particular campaign. What you see in this slide are some Google Earth images. On the upper left is a broad scale image of the different areas where we flew the missions. In the bottom left, if you can see, it mentions controlled releases and the flare stack. The flare stack is what I'm going to focus on for today. And if you see the two greenish rectangles towards the right, that's where we flew missions over a landfill and some factories and some other agricultural areas. So the goal here was to just sort of see what could be done with the system in these different types of modes and over these different geographical areas. So in the bottom image, you see a blow up of the wastewater treatment plant. You can see the 3 circular areas. Those are the water storage tanks where they're processing the water, and then the flare stack is called out in the green text in the bottom image. That's where I'm focusing today, on the data that we collected. So bottom line is we spent a day training them, doing the planning, installed the system, and then the pilot flew the aircraft, the Cessna, and beside him was an operating technician who controlled the laptop, and all he had to do was just really press go, and the system did all the work. So this just gives you a sense of the types of missions that we flew during this campaign. But this next slide gives you an idea of the types of results that are generated in real time. So let me spend some time on this slide. So in the image on the left, what you see is the infrared image just above the flare stack. And the left part of the image, you see a portion of one of the water storage tanks. The green pixels you see in the image, that's methane. That's methane that was detected and identified at the individual pixels within this hypercube that you're seeing in the image as the pilot flew over it in targeting mode for a single frame. And this slide gives you an idea of the real-time results that the operating technician can see as the flight is being conducted. So you see the greenish color, the pixels. It shows to the right, it's methane. It indicates how many pixels within the image contained methane. It gives an approximation of the area on the ground where this methane covered within the image. And then some other information which indicates the data time stamping, but also the AGL. This was about 300 meters or about 1,000 feet AGL, and the bearings in terms of their coordinates. So very simple, very straightforward results to show if I see green pixels, there's methane. And in this case, the operators of the plant may not know there's methane being generated from this flare stack because maybe they assume they're getting full combustion and not releasing any fugitive methane. But the data doesn't lie, the spectra do not lie. Clearly, methane is being generated. So just to give you an idea of what can be seen in real time as you're flying these missions. Okay, so that's detection and identification. A question always comes up when we talk to clients about this type of capability. What's your detection limit? How low can you go? And unfortunately, the short answer is it depends, because detection limits are dynamic and they're a function of many different factors. And this is just science that dictates this. The key factor in determining detection limit is something we call thermal contrast. And all that means is the difference in temperature between the gas of interest, in this case methane, and the background in the measurement. In the case that I showed you in the previous slide, that would be the asphalt that is in the pavement below the aircraft, and the various other elements within the scene. So thermal contrast is key. The higher the thermal contrast, the greater you can detect materials and the more sensitive you can be. But there are other parameters: spectral resolution and integration time. I didn't mention integration time earlier, but spectral resolution and integration time are two factors you consider in pre-planning. As I said, we did these measurements at 10 wave number resolution, and integration times are typically on the order of microseconds to milliseconds. And really what that comes down to is how noisy is your signal? How fast do you want to fly? How low do you want the noise to be in the signal? You weigh all that out. So those are very key parameters in determining detection limit. And then some others that are listed here in terms of the flight planning. Now, when we talk about detection limits, we actually can express this in two different ways. One is called the column depth, which is the parts per million by meter. And all that means is parts per million over the depth of the gas being investigated. In the lab, we can control that depth using a gas cell. In an aircraft, we can't do that. We don't know exactly how deep the column is. So typically, column depth, ppm meter, is a way to express this. The other is the leak rate, which may be of more interest to you, which is mass per unit time, grams per second or kilograms per hour. And we can estimate this from the measurement of the signal and known the molar mass of the gas being detected, plus the speed of the aircraft and the time of acquisition. So those are a couple ways we can express this. What I want to show here is a picture of a detection limit estimator tool that we use at Telops, that we developed in pre-planning to help you understand, okay, I want to be able to detect, for example, 5 grams per second of a leak rate. We'll figure out how high do you need to be or how low do you need to be in the flight. What should the wind speed be? What should the air temperature be? And so on and so forth. We can calculate this and give you a sense of what you can expect. But typically 1 to 10 grams per second is something that can be expected in terms of a detection limit. So what I show in this next slide is an example of a figure that comes from a final report. And this is actually part of the report we sent to Skycam after our measurements. Now, this is maybe a confusing slide, but let me just walk you through the basic steps. First of all, think of this as a metadata analysis. So statistics of statistics. And for this particular slide, it represents over 2,500 scenes that were collected during a particular flight and 22 kilometers of flight area. Now, what you see here are different colors of curves on the graph, the yellow, the red, and the blue. What they represent are the amount of the pixels in the scene that contains some signal. Okay, so the way you interpret this graph is you look at, okay, if I want to obtain a certain detection limit and I chose 1 gram per second, what percent of the image area needs to be filled with the gas of interest? And as you can see, as I take the dotted line going vertically and I go up and go over, the blue line indicates that 75% of the image area would have to be filled with signal for about 18% of the total scenes. As I go up, you can see that if less of the image area is filled with signal, I need more scenes that have that signal because it comes down to signal averaging and statistics. So the bottom line is this. When you ask the question, what's the detection limit? The answer is, it depends. And furthermore, we as teleops will work with you to determine what are the right parameters, both instrumental and flight planning, to help you achieve the detection limit that you need for your mission. As I start to wrap up, I just want to talk about where things are going in the future. And what you see here is the next generation of an airborne solution, which is in development at teleops. But this is a drone-based HyperCam system, as you see in the photo on the upper left. And the idea here is a smaller, lighter, lower SWaP, size, weight, performance platform or power platform that can do the same capabilities as the system I described, but in a smaller package. So this is where things are going. The other nice thing about this newer system, I mentioned very early on, there are black bodies integrated into the HyperCam Mini for calibration. This system has a permanent calibration, which is a feature of our broadband cameras that we've offered for many years. And again, using our software, we'll do automated gas detection identification. Just need to say, this is in development. This is coming down the pipe, but this will let you know kind of where things are going in the future of airborne methane detection measurements. So, what's the story I hope I told today? Some of the key takeaways. teleops, industry leader in high performance infrared cameras. Hyperspectral infrared imaging is a very powerful technique in the scientific community. It's recognized as a high fidelity, high reproducible technique, and is amenable to many of the LDAR applications we discussed today. We offer a service where we can work with you as a team to do these measurements and provide the reports that you need. And I discussed some of the results we got, particularly from the flare stack over the wastewater treatment plant at that facility in Livermore, California in February of this year. So it's a very powerful technique, and I encourage you to consider it and look into it as you're deciding what you need for your operations and your business. So I just want to acknowledge some of my coworkers, Martin Chamberlain, Marc-Andre Albert, and David Gendron. They're all teleops engineers. They were on site at Skycam during the measurement campaign and did a lot of the data workup and post-processing. But also Chris Dombrowski of Skycam. There were other individuals involved there, but he was the key person with whom we interfaced and helped us set up these measurements. And of course, the Energy Conference Network for hosting this webinar today. So with that, I'm going to leave you with some contact information about how you can learn more about teleops and the services we offer on our website at teleops.com. We have a section which discusses the methane measurement services, but feel free to send us an email or give us a call anytime you'd like. So that's my presentation for today. And what I'm going to do is see if we have any questions in the Q&A. So one question that came up was about the GPS on the back window of the aircraft. I can't go back to that slide, but in the back of the aircraft, there is a window, as you can imagine, that was mounted with a suction cup mount. And actually what we did and what we do is then calibrate the position of that antenna to the actual position of the system so that we know down to the centimeter where they are relative to one another. So that's how we get the more accurate location measurements. But it's fairly straightforward to do that mounting. Sensitivity of the sensor, I did discuss the detection limits and the flow rates and what we can achieve. Again, on the order of 1 to 10 grams per second, but it's very dependent on all the factors I described. So can't give you a single number, but that should give you an order of estimate of what you can be able to achieve with that this type of system. Temperature limitations is another question. So the operating temperature range for the system is -10 to +50 Celsius. Okay. Storage temperature is wider, but that gives you a sense of the operating temperature. I mean, it is an FTIR system. There is a cooler for the detector. It's a Stirling cooler, so it's a closed cycle compressor. So above 50 Celsius, it has challenges maintaining the detector temperature, but -10 to +50 should give you a sense of the operating range. Another question about streaming the data in real time, the streaming protocol. That's a great question. I didn't get into that. So the way the HyperCam Airborne Mini works, as I showed in one slide, is there's the optical head, which is mounted on the stabilization platform. There's a separate control and processing box. Those are connected via 10 gig Ethernet connection. So all the data is streamed to the CPB in real time. Now the laptop is connected to the CPB by a 1 gig connection, and that's really just for control of the system. The way we work with the data and manage it, we don't stream the data in real time. There is a removable 4 terabyte SSD on the CPB that once the flight is completed, it's taken off, offloaded to a separate computer processing. But 10 gig from the optical head to the CPB, then offloaded separately for processing. Question about, is the detection limit better if the flight is slower and closer to the ground? Okay, so let me talk about speed. Slower, is better. 70 knots is what they flew on the mission I described here. But it's not necessary that you fly particularly slow. Again, airspeed of the aircraft is figured into the detection limit calculation. Closer to the ground, it's interesting that that question came up because the system actually has an aperture that protects the optical window that doesn't open until 100 meters of elevation, AGL, is achieved. So got to be at least 100 meters. We flew at 300 and 450 meters. So I think that's typical for these types of missions. But certainly if you're at 20,000 feet, for example, like a commercial aircraft, that would be very challenging. But again, all that's figured into the calculations. I'm looking at the questions now. And I'm scrolling through. Why use an FTIR, not a focal plane? So the question is, why use an FTIR and not a focal plane? I'll actually address that this way. So the FTIR is the mechanism by which we analyze the incoming wavelengths. Okay, so if you will, it scans the wavelengths in time. That's the interferogram. And then we compute that into wave number space to get the spectrum. The focal plane array is the detector. So the detector is a 320 by 256 FPA. It doesn't care that there's an FTIR there. It could be any other type of wavelength analyzing system. So there are really two different components. But FTIR allows us, as I said in a previous slide, to get relatively fast scanning, very high spectral resolution, and relatively low signal to noise. Okay, I'm looking at the questions. Question is, do we evaluate methane by absorption or emission? Another good question. So absorption and emission are two phenomena which occur in materials in the atmosphere. And, you know, it really depends on the background and the temperature of the background relative to the temperature of the gas. So if the gas is colder than the background, we see absorption. If the gas is hotter than the background, we see emission. The software and the detection identification algorithm doesn't care, because to put it quite plainly, the peaks either go down or they go up. So it's really evaluating the shapes of the peaks and the intensities of the peaks, not so much the direction. So that's kind of how we deal with that. I'll take one more question and then we'll wrap up. Are there weather restrictions that can limit your conditions? That's a great question. I'm glad that that was asked. Yeah, so because we're doing passive infrared measurements, as I said, the background thermal contrast is key. If it's raining and cloudy, not a good day to fly these measurements. The ideal day is a cool day, clear sky, clear background. And again, ideally, depending on what you're flying over, whether it's asphalt or grass in the case of a landfill, we have to take that into consideration. So weather conditions actually are very important: air temperature, ground temperature, and all that. So that's something that we need to consider when we're doing our flight planning. So yeah, there are certain conditions under which doing these type of measurements aren't feasible, but that's something we can help you with. So that's all the time we have. I apologize, I couldn't get to all your questions, but these are some great questions, and I believe any that we didn't get answered, we can address those in a follow-up after the webinar. So I want to thank you, everyone, for your time today, and I'll turn it over to Jessica to wrap things up.
Well, thank you so much, Dr. Norman, for that presentation, and thank you all for taking the time out of your day to join us. Have a wonderful day.